Okay. Good morning friends, welcome to the next lecture of energy conservation and waste heat recovery. And today what we will do is, we will start from where we left off in the last lecture when we were discussing thermo-ionic generators. Remember again, thermo-ionic generator, if we recall, is a direct conversion device whereby we can use thermal energy and directly convert it to electrical energy without having to depend on any moving parts, any mechanical conversion and so on. Okay. So, as we saw last time and just to recap looking at this PowerPoint slide, it is a direct conversion device. It consists of two electrodes. The first one is an emitter, and which when heated to sufficiently high temperature will emit electrons. Okay. And the reason why it emits electrons or it emits electrons is because at a certain high, at sufficiently high temperature, some of the electrons have sufficiently high kinetic energy, which is above the what we defined as work function for that material, and these electrons therefore as it attains energy above the work function can detach from the surface and move towards the collector surface. The collector is at significantly lower temperature and therefore as it receives the electrons, what happens is the electrons give up their energy and come down to the level of the Fermi, which is known as the Fermi level of the collector surface. So, in the process it gives up thermal energy, which is rejected as heat from the collector surface. Okay. Now, as we saw last time, the emitter and collector materials are chosen such that the Fermi level of the collector is higher than that of the emitter. So, therefore, what happens is the electrons that are now collected at the collector surface has higher Fermi level, which is the stable state, than that of the emitter. So, therefore, now if we connect the collector and the emitter externally, the electrons will tend to flow through the external load. Okay. So, this is what we saw here. If you look at the sketch that I have drawn, this is similar to what we drew last time. This is the at the collector surface, at the emitter surface, what happens, the electrons attain an energy level which is equal to the work function or higher than that, and so therefore it detaches and comes towards the collector, where it settles down to this level, which is the Fermi level. Now, this Fermi level of the collector is higher than that of the emitter. So, therefore, as we the electron, since, let me write down, since epsilon f of c is greater than epsilon f of E, the electrons flow from collector to emitter. Through an external load. If you connect the collector and emitter, what we will see is, if we close the circuit, then we will have an external current flow from the collector surface to the emitter surface. Okay. So, therefore, what happens is, as the current starts to flow, then what happens? There is a voltage that develops between the two, which will depend on the value of the resistance that we, of the load that we have connected. Okay. So, let us call that V naught. Okay. So, V naught is the voltage that builds up across the external load RL. Now, what is RL? Again recall, maybe from the slide itself, we see that the RL is this external load, and the VL is the voltage that we will measure once the current starts flowing from emitter to collector. Remember, the electrons are flowing from collector to emitter, therefore, the direction of current flow will be the direction of electron holes, or in the opposite to that of the electrons, which is from emitter to collector. So, this is how we get electrical energy out, as we saw. Clear? So far so good, but what happens is the following. Let us come back here. So, there are certain other things that we need to keep in mind. Okay. So, as the current, this is what we call the space charge effect. Clear? So, what happens? As the electrons start flowing from the emitter to the collector, there will be a build up of the negative electron cloud in this interelectrode space. Clear? and so this is going to slow down the movement of the electron from the emitter surface to the collector surface. Okay. So, I repeat this again, as the electrons start flowing from the emitter towards the collector, there will be what we call an electron cloud that will form in the inter electrode space, and the net effect of this is to slow down the movement of electrons from the collector, from the emitter to the collector. Okay. Apart from that, see, as the electrons dissociate from the emitter surface, the emitter becomes positively charged. So, therefore, the attractive force, it will tend to attract the opposite charged electrons, the negatively charged electrons towards it, and this will also slow down. Okay. So, these two actually oppose the thermoionic generation, okay, the build up of the voltage of the thermoionic generation or the current flow. All right. So, therefore, just having that energy level at the work function of the emitter, it may be okay to initiate the thermoionic generation, but to sustain it, it is not going to be enough. So, therefore, in reality what happens is, we are going to need these the energy level to go higher than just the work function. Okay. So, actually the electrons have to go to a higher level and then come down like this. Okay. And why is this required? Because of what we call space charge effect. Space charge effect. What is it? Number 1, the electron cloud in the inter electrode space, and number 2, attractive force from positively charged emitter on the free electrons. Okay. So, therefore, what is the net effect? Net effect is there is an additional potential that is required. Okay. So, there is an additional potential that is required, and that is called, we will denote it as delta V E B. Okay. This is also called sometimes as barrier index. Just it helps to know these names. Okay. So, what happens, I will now write it down. So, this therefore, this additional potential is delta V E B, the barrier index. Clear? So, the barrier index of the emitter. So, therefore, we will accordingly call this as delta V C B. Clear? Then what happens? There will be some losses because of the connecting wires and leads. So, we will call it delta V small l, and the rest will be delta V L. So, let me write it down. Delta V L is voltage or potential difference across R L, which is external load, okay, and delta V small l is drop or voltage drop across the leads or connecting wires. Okay. So, finally, this is what we are going to get and it is going to depend on the value of the current. Okay. So, there are additional physics that will, from where Richardson-Dushman equation, from where we can get the charge density and so on, but we are not going to get into all that all those details as part of this course. It suffices, we have I think a fair understanding based on the discussion that how the thermionic generation works, what happens, what is it that gives rise to this current flow when we heat the emitter surface to sufficiently high levels, and we saw that. Why it does it? Because some of the electrons from the emitter surface attain enough energy to overcome the work function and therefore goes towards the collector, whose Fermi level is higher than that of the emitter. So, therefore, if you now connect an external load, the electrons will flow from the collector to the emitter. Through the interelectrode space, the movement is from emitter to collector. Through the external load, when you close the loop, the movement of electrons is from collector to emitter. So, therefore, which essentially means there is a current flow from the emitter to the collector, and if you now attach an external load, you can get electrical energy out of it. Okay. And then we saw a few things about the about the different energy or the potential levels that are required. We talked about space charge effect, for which you need an additional potential beyond the work function, so that the thermionic generation can be sustained. All right. So, this kind of wraps up our discussion on thermoionic generation. Okay. So, what we will do next is we will study a fourth type of direct conversion device, which is even though this one started or was first proposed and shown to work in 1960s, but however, the research on this was limited, and it is only the last 10 years that research has really picked up. Okay. So, this class of direct conversion device is known as thermophotovoltaic. Okay. So, let me write it down. Thermophotovoltaic generation, or TPV. So, this one actually what we will do is, we are not going to get too much into physics or mathematics. We are going to limit ourselves only to how this functions, what are the components and so on. Okay. So, what is a thermophotovoltaic? Let us look into this. So, thermophotovoltaic, as the word photovoltaic suggests, it works on the same principle as a traditional photovoltaic cell. Now, photovoltaic cell, I think most of us have seen the solar collectors on our rooftops, which are primarily photovoltaics. What it happens is, a photovoltaic cell essentially is a PN junction. The input to the PN junction is optical energy. So, as the photovoltaic name suggests, these cells, these PN junctions, as it receives optical energy, it can generate and separate electron hole pairs, and this is how it generates electricity. Okay. So, photovoltaic, as the name suggests, photo to volts, which means a direct conversion of optical energy. So, therefore, photons to electricity. Clear? So, this is how the photovoltaic works, as we know, in a very nutshell. So, what is thermophotovoltaic? Thermophotovoltaic actually works on the same principle as photovoltaics, but the only difference here is the optical energy that the photovoltaic cell receives is not from the sun, or the source of the optical energy is not solar energy, but however, it is thermal energy. Okay. So, what do I mean by that? So, here also we have a certain material or a surface which is an emitter. Okay. Similar to thermionic, in thermophotovoltaic also we have an emitter. Here also we have to heat it up to sufficiently high temperature. Okay. But what is the difference here? The difference is, these surfaces, this thermophotovoltaic, or the surfaces that the emitter surface used for thermophotovoltaic generation, at that sufficiently high temperature emits photons. Okay. So, what is emitted, unlike electrons in thermoionic, in this case the emitter surface emits photons, okay, or packets of light energy. So, at high temperature, so a TPV system or thermophotovoltaic generator system, therefore, at a minimum consists of an emitter which is at an elevated temperature. So, I have shown a range of temperature which typically works in the infrared region. So, you need an emitter which is heated to an elevated temperature and has the properties where at those temperatures it can emit photons. And then you have a photovoltaic power converter which is the PV cell, which receives those photons and converts it to electricity. Okay. But however, these are the two minimum components, but typically what we have is we also have some additional components like filters, concentrators, reflectors, etc., which we are going to talk about. Okay. So, again once again if I have to define it in a nutshell, thermophotovoltaic is again photovoltaic conversion where we use semiconductor and PN junctions to generate electricity from optical energy. The difference here is that the source of that optical energy is not sun or solar energy, but it is photons that are emitted from an emitter surface which is heated to a highly elevated to an elevated temperature. Okay. So, as is shown in this slide, this is what we are seeing here, that if the surface is heated to sufficiently high temperature, then the surface is able to emit photons, okay, which will be then absorbed or by the photovoltaic power converter. Clear? So, what we will do next is some additional points. So, what is this emitter surface? The emitter surface can be a solid material, but more importantly the research that is happening is going towards engineered surface. So, that why engineered surface? This is because the thermal emission characteristics of the emitter surface, in order to maximize or optimize the performance of the thermophotovoltaic generator and minimize losses, the thermal emission characteristics has to be matched with the absorption characteristics of the photovoltaic cell. Okay. So, something is emitted, okay, from our knowledge of, let us say, radiation heat transfer, right. When you have electromagnetic radiation, what are the different properties? The radiation happens across all wavelengths, but definitely at certain wavelengths it is higher than at other wavelengths, right. So, when we talk about thermal emission characteristics of a surface, we mean it is a spectrum over a wavelength, over a range of wavelength. It also has directional properties, clear, right. So, it is emitted in all directions across 360 degrees, there is polarization and so on. So, an emitter surface will have its own emission characteristics, and the absorption the surface which is absorbing here, in this case the photovoltaic cell, will have its own absorption characteristics. So, the best match is when the emission characteristics of the emitter surface matches with the absorption characteristics of the photovoltaic cell, because our aim is whatever is emitted should be absorbed, and that is what will give it the maximum efficiency or minimum losses. Okay. So, in order to do that, of course, engineered surface treatment, etc., is important, but also sometimes what we use is, or not sometimes, people are looking at it, use filters and surface treatment to get selective emission characteristics, etc. So, these are all being done today to increase the efficiency and minimize losses, so that most of the emission that happens from the emitter surface is absorbed at the photovoltaic cell. Okay. There are also these photovoltaic reflectors, etc. There are lot of new research that across different groups, including MIT, Texas Austin, and several other universities where this research is happening. Okay. So, it is a very interesting field right now. It has lots of it has great application, I would say, in waste heat recovery, clear. But unlike or rather similar to most other direct conversion devices, the efficiency, if we just look at the efficiency of the amount of thermal energy that we need to give to the emitter surface versus the amount of electrical energy that we are able to extract out of it, if we define the efficiency in those terms, the efficiencies are low. Okay. When we say low, it is maybe 10% or in around about that range. So, definitely it cannot replace, you cannot think of this to replace our traditional power plants or even other means of generation of electricity, but however this is ideal, but this is very good, it is very good for auxiliary power generation from waste heat. Okay. So, if you are in a regular power plant, similar to all the other direct conversion devices that we talked about, if you are wasting a lot of energy in the form of thermal energy, use that to heat up the emitter surface. Okay. And as you heat it up, and if you are able to reach the temperature range like 900 to 1300 is one range that I talked about, if you are able to reach the temperature range where the emitter surface starts emitting photons, and you engineer the surface such that the emission characteristics are close to that of the absorption characteristics of the photovoltaic cell, then we will be able to convert the electricity or convert the emitted or whatever is the emitted photons to electricity directly at the PV cell. Okay. All right. So, that kind of brings us to the end of this section or discussion on direct conversion devices. Okay. Let us do a recap of what we discussed as part of direct conversion device. We started by saying that the direct conversion devices are means, direct conversion devices are means by which, or are technologies by which we can convert thermal energy directly to electrical energy. Okay. Now, what is so great about this? Remember, in a regular power plant, okay, steam turbine cycle, the energy input is in the form of fuel which is burnt. So, that is heat energy, thermal energy. But what do we do with that? We use that thermal energy to heat up a working fluid which flows through a turbine in the vapor form and rotates the turbine to generate mechanical energy. Okay. The mechanical energy, the rotating turbine is then converted to electrical energy through a generator. Okay. So, fuel, heat, mechanical energy, then electrical energy. So, in this case what happens is I already have the thermal energy. In direct conversion device I already have thermal energy which I supply to this direct conversion device and get electricity out of it. No moving parts, no working fluid. Clear? So, as part of this we started by discussing the first technology, which is thermoelectric generation. So, what was thermoelectric generation? It was a P and N junction. Okay. It is a P and one P doped or positively doped semiconductor, one negatively doped semiconductor, which are connected electrically in series and thermally in parallel, and we have a series of them. So, what we do is on one side we apply the waste heat source that we have, so that the temperature is elevated. The other end of the thermoelectric device, or these PN junction pairs or the PN pairs, thermoelectric pairs, that is maintained at a lower temperature. So, this temperature gradient that happens across the thermoelectric device results in the generation of electricity, because the charge carriers, which is holes in case of the P doped semiconductor and electrons in the case of N doped semiconductors, tend to move due to their higher energy levels, will tend to move from the hot junction towards the cold junction. Okay. So, we started, this is how a thermoelectric generator works, and what we did next was we did a lot of analysis to calculate the efficiency of these thermoelectric generators, to figure out under what conditions we can maximize the efficiency, we can maximize the work output, which do not necessarily mean the same, and so on, right. And we also talked about applications of thermoelectric generators, and one of the things, very interesting ones that we saw was it has been already in use in space shuttles. Okay. In Apollo and Mars mover it has been there, because there the cold temperature is readily available, because outer space is at very low temperature, 3 to 5 Kelvin, right, and the heat source was given through radioactive reactions. Okay. So, that was thermoelectric generator which we studied. Okay. I also talked about a research story where bismuth telluride was able to give high Z value. How? Because we were able to grow it at nanoscale, where the electrical conductivity was kept constant and the thermal conductivity went down, because the phonons could not pass through, whereas electrons could pass through those length scales, right. So, that was a slight research story, but very interesting one that we talked about. Okay. The next technology that we discussed was magnetohydrodynamic or MHD generation. Magnetohydrodynamic depends on or works on the principle of Faraday's laws of electromagnetic induction, where what we said is if an electrical conductor and a magnetic field move relative to each other, it gives rise to an electric field in the third direction. So, in an MHD duct or magnetohydrodynamic generator duct, what happens is we have these high temperature gases which when heated to sufficiently high temperature will emit electrons. Okay, these are gases emitting electrons, but the amount of temperature that you need is very high. So, we seed it with small seeding alkaline or cesium vapors or small seed, we seed the combustion gases with very low concentration 1% or so, so that this emission of electrons happen at a much lower level. And again, when if you say lower level, we are talking about 3000 Kelvin. Okay. And then we say that we are going to make this ionized gas move through a duct across which we apply a magnetic field, and then and as a result what we have is we have a magnetic field and a conductor moving relative to each other, and therefore from the other two walls we could generate a DC current or DC voltage. All right. And how is this going to help us? We said that the modern furnaces can reach temperatures of up to 300 Kelvin, but however the gas or the steam turbines or even gas turbines that are used in industrial applications, we are typically limited due to material constraints to around 1000 Kelvin or so. So, therefore, we are not being able to utilize the high temperatures that we can go, that the furnace technologies allow us to go to. So, this is one case where we can have combustion at very high temperature, generate the gases at around 300 Kelvin, use a magnetohydrodynamic generator to generate some electricity, and let the gas come down to temperatures below 200 Kelvin where it loses its ionization potential, and thereafter use that combustion gas for heating up the water in the boiler and convert it to steam, and also for air preheating. Okay. So, that was magnetohydrodynamic generation, second one. Next what we studied was thermo-ionic generation. Here also you have an emitter surface which is a material, a solid, which is heated to high temperature, and at that high temperature when some of the free electrons or the outer electrons attain energy levels higher than that of the work function corresponding to that material, it goes to a small gap towards another material which we call the collector, which is at a significantly lower temperature where it gets collected. The emitter and collector are chosen such that the Fermi levels of the collector is higher than that of the emitter. So, therefore, when the collector collects these electrons, it is at a higher potential, and so if we now attach an external load across the collector and the emitter, we will have an external current flow from the emitter to collector. Okay. And this is how we get electrical energy out of it, right. And finally, the fourth technology that we talked about is thermophotovoltaic generation. Here also you have an emitter and a collector. The collector is a photovoltaic cell, it is a PN junction, it works on the same principle as that of a solar photovoltaic, right. Except that the optical energy in this case is provided by the emitter surface, which when sufficiently heated emits photons. Remember, in thermoionic it emitted electrons, here it emits photons. And then what we do is the research today is on so that the emission characteristics of the emitter surface matches with the absorption characteristics of the PV surface, so that we have a very efficient conversion of the emitted photons to electricity. So, it is an efficient conversion of the photons. However, the process of converting thermal energy to electrical energy still is inefficient. Efficiencies are much lower compared to even conventional power plants. So, therefore, any of these technologies, be it thermoelectric, thermoionic, thermophotovoltaic or MHD, none of these, MHD is a little different however, but the other three at least, none of these can replace conventional power plants. However, all these are very useful, can be viewed as very useful options if we want to convert the waste heat from a power plant to electricity. Okay. So, additional generation of electricity is possible through all these techniques. Okay. And last point that I want to make that is true for all these four technologies is these are all essentially heat engines, and therefore, their maximum efficiencies are limited by Carnot efficiency. Okay. All right. So, with that we come to an end on this section on direct conversion devices, where we studied 4 different technologies, and in the next lecture what we will do is we will move on to a new topic. Okay. So, thank you very much, and we will meet you in the next lecture.